Hi everyone, today we're going to talk about the fast Fourier transform, or FFT. So in digital signal processing, we often need to change a signal from the time domain to the frequency domain. The tool we use for that is called the discrete Fourier transform, or DFT. FFT is basically a faster algorithm to calculate the same DFT. Same results, but much quicker. And that's the whole purpose of FFT, efficiency. Now why do we need something faster? Because the normal DFT is computationally expensive. If you have n samples, the DFT needs about n squared complex multiplications. So when n gets bigger, let's say 1,000 or 10,000 samples, the number of calculations grow very fast. This makes DFT slow and impractical for real-time or large-scale applications. This is where FFT comes in. Instead of n squared operations, FFT only needs about n log n operations. This might not sound like a big difference, but for large n, it's huge. For example, with 1024 samples, DFT needs around 1 million operations, but FFT only needs about 10,000. So FFT can be 100 times faster or more, depending on the size of n. So how does FFT actually achieve this speed up? The main idea is called divide and conquer. FFT splits the input signal into two smaller groups, one group with the even index samples and one group with odd index samples. Each smaller group is then solved separately, and this splitting keeps happening recursively until the problem becomes very small and simple to compute. Then, the results are combined back together. This combining step is done using something called the butterfly structure. It's called a butterfly because when you draw the signal flow diagram, it looks like a butterfly shape. Each butterfly takes two input, multiplies one of them by a twiddle factor, then adds and subtracts them to get two outputs. This structure is repeated stage by stage, and is what allows FFT to reuse calculations efficiently instead of repeating them, which is why FFT is so much faster than direct DFT. FFT is used everywhere in real life. Some examples include audio processing, like equalizers and noise cancellation in headphones. Second, in image compression, such as JPEG, which uses frequency transform to reduce file size. Next, in wireless communication systems like Wi-Fi and 4G and 5G, where FFT is used in OFDM to process signals efficiently. Those are just a few. FFT is really a core building block in modern electronics. Now, I'll explain questions A to E of our FFT examples. For question A, we are asked to calculate the DTFT magnitude response of the input signal, which is xn equals to 1, -1, 1, -1. First, we express the signal using delta functions and substitute it into the DTFT equation. Replace omega with 0.25 pi and evaluate each exponential term using Euler's identity, where the complex exponential is written as cosine omega plus j sine omega. After simplifying the complex numbers, we obtain the frequency response and finally calculate its magnitude. The final answer is its absolute value of x when frequency is 0.25 pi equals to 1.082. For questions B, we solve the same problem using an 8-point DFT instead of the DTFT. We first convert the frequency value into the corresponding DFT index using the relationship omega equals to 2 pi k divided by n. Since n equals 8 and omega equals to 0.25 pi, we obtain k equals to 1. We then substitute this value into the DFT equation, and the magnitude is again 1.082, showing that the DFT matches the DTFT results at the sampled frequency. For question C, we compute the 4-point FFT using the radix 2 butterfly diagram. The input sequence is first arranged in bit reverse order, which is x0, x2, and then x1, x3. Then processed through two butterfly stages. Stage 1 performs 2-point butterfly, while Stage 2 combines the results using the appropriate twiddle factors, such as 1 and -j. For questions D, there are three reasons why the radix 2 FFT is much faster. First, it uses a divide and conquer strategy to split a large DFT into smaller ones. Second, it exploits the symmetry and periodicity of the twiddle factors, allowing repeated calculations to be reused. Finally, it performs in-place computation, reducing both memory usage and computational overhead. Finally, for questions E, the FFT achieves its efficiency by recursively separating the input into even and odd samples, reducing the computational complexity from O n to the power of 2 for the DFT to O n log 2 n. However, one disadvantage is the radix 2 FFT requires the input length to be a power of 2, so signals with other lengths often need zero padding, which can slightly affect the signal representation. Thank you.